Hello, my name is Jacob, and I'll be reviewing the paper From Statistical Model Checking to Runtime Monitoring Using Bayesian Network Approach by Jaeger, Larson, and Thibault from Aalborg University. To begin, with the ever-increasing complexity of cyber-physical systems, the need for online monitoring becomes more critical to ensure system reliability, reduce risk, and assure behavior in real time. Common approaches to modeling these systems are with stochastic timed automata, which are checked using statistical model checking engines, or SMCs. SMCs, however, have a couple drawbacks in their ability to verify complex systems and in real-time applications. Therefore, we introduce SMC to Bayesian networks for online monitors. As previously mentioned, with the limited flexibility that hinders SMCs, a Bayesian network approach absorbs a lot of the complexities and inefficiencies so that we're able to focus on real-time observations of the system properties. A couple societal impacts include a new reliable method to evaluate real-time systems with unobservable properties, which results in a safer and more reliable cyber-physical system. Additionally, complex systems that have critical properties are more capable of being modeled and effectively evaluated online. With that, we move on to the problem formulation. To formalize the problem, the use of statistical model checking engines to verify properties of stochastic timed automata has several drawbacks. The first being that SMCs are not ideal for real-time probabilistic querying at system runtime due to the case that they rely on the number of sample runs generated from an STA, which can become computationally inefficient. Furthermore, SMCs are unable to assert probabilistic estimation on partial observations of the system as they require the current number of observations. From this work, we were able to derive the following contributions. The first being that we're able to generate a custom Bayesian network from the provided stochastic timed automata model using machine learning algorithms. Additionally, we're able to enable querying of system properties that are conditioned on more complex observations at runtime. And thirdly, the Bayesian network approach is computationally more efficient and accurate in comparison to the SMC. We will now move on to runtime monitoring with Bayesian networks. Within Figure 1, we see the framework for converting an SMC to a Bayesian network runtime monitor. In the top left, we start with a stochastic timed automata model, which can be represented within an SMC, in which we extract a finite set of properties, each represented by an individual monitor. This is then run on a simulator k times to produce the data necessary to train our Bayesian network. In the training stage, there are two steps, structure learning and parameter learning. Structure learning is responsible for constructing the Bayesian network graph, and parameter learning is responsible for optimizing this graph. Within the inference step, we have a resulting Bayesian network model in which we can provide a query variable and the set of observed values to then produce a conditional probability distribution that we are interested in. With the framework covered, the resulting Bayesian network is essentially an acyclic graph with the following set of elements. Phi, or nodes, are categorical random variables, or in other words, the key system properties we are interested in, and E, or the edges, are dependencies between these key system properties. In Figure 2, we can see a resulting Bayesian network after training the structure and parameters on 4 total key properties. The resulting edges showcase the dependencies between each property. We now move on to the experiments section. While there are 3 applications within the paper, we'll be looking at the bridge crossing scenario. Within this scenario, we are provided with 2 vehicles, a car and a ship, both with a goal to cross the bridge. For the car to cross, the bridge must be lowered, and for the ship to cross, the bridge must be raised. To begin, we represent the system as a stochastic timed automata in SMC. From there, we can then run 10,000 model simulations to train our Bayesian network. After training our Bayesian network, we can then run our query of runtime forecasting on the number of evolutions we are interested in. Within Figure 4, this represents, after training the Bayesian network, the resulting graph structure and dependencies between each key property of the system. With the resulting Bayesian network model, we can then run this on a real-time application to observe our query of runtime forecasting. At t0, we can see the probability that the car reaches its end location is 0.10 for every timestamp. At t1, after observing that the car waits, this changes. More importantly, at t2, after observing the property that the ship waits, the probability that the car reaches its end location has a higher chance in the early stages. After each new observation, this justifies this belief. Additionally, we observed the efficiency of these queries and noticed that the average computation time is 0.08 plus or minus 0.05 seconds, which is more than quick enough to run on a real-time system. We will now look at the conclusion of this work. To reiterate, there are a couple drawbacks to SMCs in which the Bayesian network approach prevails. The first being that we're able to train a custom Bayesian network from a provided STA model. Second being that we're able to query system properties that are conditioned on more complex observations. And thirdly, the Bayesian network approach is computationally more efficient than the SMC counterpart. Thank you.